Okay, so it looks, no, I think, can I ask everybody to mute? All right, cool. So I'm going to go ahead and start. Hello and Happy New Year. Thanks for joining us for the first CGD seminar of 2023. To begin, I'd like to remind everyone about the code of conduct for CGD. So please keep in mind our norms, especially at the end of the session when we take questions for today's speaker. So it is now my pleasure to introduce Karthik Kashinath from NVIDIA, who will be presenting towards digital twins for NVIDIA's Earth-2 initiative, pushing the limits of Fourier neural operator and transformer models for Earth system emulation. So Karthik is a principal scientist and technologist at NVIDIA. He leads various machine learning initiatives for Earth system science and CFD applications, including for NVIDIA's Earth-2 initiative, which aims at building digital twins of the Earth. For several years, he led various climate informatics and machine learning projects at the Big Data Center at NERSC in the Lawrence Berkeley Lab. And his research generally uses the power of machine learning to accelerate scientific discovery and produce actionable information in weather and climate science. So now, Karthik, I invite you to share your screen when you're ready and to begin your presentation. Thank you.
Yeah, thank you for that kind of introduction, Monica. And I will share my screen in a sec. Do you see my screen?
So we do, but we see there. That's good.
Okay, perfect. I can get started when we're ready.
Yeah, please go ahead.
Okay, great. Well, thanks everyone for joining this first week of the year. I hope you had a nice break and welcome back. I am Karthik and I'm a principal scientist and engineer at NVIDIA. And as Monica mentioned, I'll be talking about Earth-2, which is a recently launched initiative for building digital twins for weather and climate science. So I'll begin with a sort of overview and a big picture of what Earth-2 is and what digital twins are and what we're trying to achieve here. And then I'll move on to some specifics on machine learning, specifically ForecastNet, a model that we've developed for weather forecasting and also extending towards climate. And then I'll move on to some of the ideas that we're developing for climate emulation, and finally, some of the technologies and platforms that we're building to enable digital twins. Okay, so just to set the context, and this is probably obvious to everyone in the room here, the future under climate change will be harsh, and we urgently need better tools to prepare for it for all kinds of things from disaster prevention to water management to crop forecasting and any number of other applications you can imagine. So high resolution climate prediction is sort of one of the ways in which we address the consequences of climate change in the future, and it is a serious computational challenge. This is a figure from a recent paper by Tapio Schneider et al. In Nature Climate Change that projects forwards in time the computational requirements of high resolution climate modeling and also looks back into the past. Today we're at about 25 kilometer resolution with a 10-minute time step. And if we take that as the baseline, storm resolving simulations at about a kilometer scale require something like 30,000x more compute. And looking forwards towards low cloud resolving models, which are really needed to quantify the uncertainties of climate projections, that would require 100-meter resolution at 0.1 seconds, which is 500 million times more compute than we have today. So clearly, we're not going to reach this with the current computing growth until about 2060, and that might be too late for us to address the serious impacts of climate change. Now, the second challenge is that it is extremely hard to interact with very high resolution climate predictions. And this is a statement from Bjorn Stevens. He says in one of his keynotes recently we can compute kilometer scale predictions today, but we can't effectively extract the information content from it, let alone interact with the information. And the estimates for a 300-year trajectory at a kilometer scale resolution is about an exabyte, so about 1,000 petabytes of data, which is practically impossible to interact with. So Earth-2 was very much inspired by Destination Earth project of the European Commission. It began as a vision of a highly interactive climate information system for serving society with next generation climate predictions. These are images from Destination Earth and a Nature climate change paper by Bjorn Stevens et al. That shows sort of what digital twins might look like in the future and why we need these high resolution climate information systems. So the idea is, imagine you could select a region of the planet. It could be an entire continent, it could be a state, say California, or maybe even a very specific region, the San Francisco Bay Area or the city of San Francisco, or maybe even a particular part of San Francisco, and then ask questions about climate change's impacts on food, health, infrastructure, energy systems, and various other applications, and receive useful visual and statistical guidance from a highly interactive future climate information system at high resolution that serves society. That's quite a mouthful there, so I'll try to unpack it. But basically, the idea is to provide high resolution climate predictions at low latency, meaning that they are fast responsive systems that can give you information fairly rapidly. But also have these systems evolve with scientific fidelity and computational ambition, fed by a library of climate predictions that are extremely high resolution that they seem impossible today. So we're talking about sub-kilometer scale global simulations. And the only way to achieve this is using a combination of physics and machine learning at HPC scale. So that's the second mission of Earth-2. So these are two missions that the world is already working hard on. And one example is the Destination Earth project from the European Commission that envisions what digital twins could look like. And they lay out some of the key elements required to achieve that. One is an interactive collaborative platform. The second is data-driven models. The third is storm resolving models, or even finer scale models than that, a unification of various different data sources and observations, and finally, exascale compute. So our CEO, Jensen Huang, was inspired by this project and said, well, we have the technical know-how to make a big difference to this global effort towards building digital twins, using sort of the full stack technologies that NVIDIA has. So the first is an interactive collaborative platform that we're building called Omniverse. It's not just for climate science, but for a wide range of applications. The second is a physics ML, so physics-inspired machine learning model platform called Modulus, which is used to build various different types of physics-informed machine learning models. GPU acceleration of various different principled numerical simulations, which NVIDIA has been doing for quite a long time. Unifying observations in various different data sources along with models in something called the Omniverse Nucleus, which I'll touch upon in a few minutes. And finally, exascale computations, which of course we've been doing for quite a while too. So Earth-2 is a highly collaborative project, and it is in collaboration with various institutions across the globe. We're bringing our AI engineering and full stack expertise to complement the research capacity that exists in academia and government. On the right are a snapshot of some of the partners that we're working with in Europe and in the US and elsewhere too. So with that introduction to Earth-2 and digital twins, I'll dive into machine learning approaches that we're developing for both weather and climate emulation. So starting off with our sort of flagship machine learning model called ForecastNet, which is now pushing the frontiers of AI-driven digital twins. On the left is an image that shows ForecastNet emulating weather dynamics across the globe at 25-kilometer resolution. On the right are some of the highlights of the model. It's a global model at 25-kilometer resolution. It emulates the entire atmosphere, fully data-driven. So as against subgrid scale models that are emulating different types of processes, this is a unified model that emulates the entire atmospheric dynamics in a single shot. It uses a combination of Fourier neural operators and transformers, which I'll get into some detail in a couple of minutes. It's at 25-kilometer global resolution, which is the native resolution of the ERA5 reanalysis dataset from ECMWF that it's trained on. One of the nice properties of the model is that it can be initialized by initial conditions from different models, including GFS. The inference time is only half a second for a 2-week forecast, and this is really where the model shines, is that it's extremely fast in inference, and it's about 5 orders of magnitude faster than traditional numerical weather prediction models. The model has been calibrated. The ensembles have a initial condition and Bayesian model uncertainty in them, and I'll talk about this as well. The speed up, as I mentioned, compared to numerical weather prediction models like IFS is between 10,000 and 100,000, depending on the resolution. The power savings corresponding to that speed up is about 4 orders of magnitude, so 10,000x. We're currently exploring some very exciting long rollouts of the model. So we're looking into predictions that are much longer than medium range forecasting. And we currently have stable simulations out to about 250 days. And it's a completely open source project. And I want to emphasize that this work is, in fact, all of the models that we're developing in Earth-2 is going to be open sourced. ForecastNet is already open sourced, and it's meant to be a highly collaborative project along with various partners. So a brief history of data-driven weather prediction, which some of you might be aware of. It's not that old. It's about 4.5, 5 years old at this point. It started off with Peter Dubin and Bauer in 2018 from ECMWF. They had a machine learning model, a simple multi-layer perceptron at about 2K pixels for each channel. And then came the Rasp et al. Paper, the Weather Bench paper in 2020, also at about 2K pixels. Jonathan Wayne and folks at 2.6K pixels, slightly higher resolution. And then the next version of their model, also in 2020, was 16K pixels. And as you can see, various different machine learning approaches have been used. Early last year, Ryan Keisler wrote a paper on using graph neural networks to emulate weather dynamics at 64K pixels. And then later that year, our paper was published at 1 megapixel, so 0.25 degree resolution global. So in just a matter of about 5 years, the resolution of these models have gone up by about 50x, and I'm sorry, 500x, and that's really massive growth in a very short period of time. And I expect that in the future, these models will be emulating dynamics at potentially kilometer scale. So what is the backbone? What are the inner workings of ForecastNet? It's based on 2 important things. One is the Fourier neural operator. It's essentially a spectral space model. It uses convolutions in spectral space instead of doing it in physical space. So you have a Fourier transform, and then you have your standard neural network operations, linear and nonlinear, and then an inverse Fourier transform. The key idea here is that it's very efficient, so you can use a few modes to characterize the dynamics. And the second is it enables global convolutions. So we're looking at correlations across all scales in space and time. On the right is a snapshot of a transformer architecture. I won't get into too much detail here, but for those of you that are aware of transformers, they're sort of all the rage in deep learning today, and they're very powerful networks that can learn complex spatiotemporal dynamics. The key property of this particular network is that the spatial mixing is done using the Fourier transform, the Fourier neural operator. So it makes the whole architecture much more efficient and also scalable on large systems. And the details of the adaptive Fourier neural operator is in the paper at the bottom. So ForecastNet, as I mentioned, is trained on 0.25 degree ERA5 data. That's the native resolution of this data set. We're currently using only a small subset of the total ERA5 atmospheric data. In particular, we're using 26 channels, and by channel, I refer to a 2D field of an atmospheric variable. On the surface, we have 10-meter winds, temperature at 2 meters, and mean sea level pressure. We have 5 vertical levels, so fairly coarse in the vertical. but we have information from velocities, temperature, geopotential, and relative humidity at the surface at 850, 500, 250, and 50 hectopascals, and integrated column water vapor as well. We're currently extending this to include many more variables. We think that radiation, surface fluxes, top of the atmosphere fluxes, vapor transport, and clouds could also be incorporated into this model. Of course, it would be harder to train and require more compute, but we expect that the predictive skill of the model would improve. The training set is from 1979 to 2015, and the validation is 2016 and 2017, and we have a held out test set 2018 onwards. So on the right are two properties of the training process that I want to highlight. The first is that we have a two-step fine-tuning process, and by this I mean that we predict one time step ahead, compute a loss, and then use the same model to predict one more time step and compute a second loss, and we optimize over both of these time steps. And just to clarify, each time step here is 6 hourly. We've tested a few other different configurations as well. On the bottom is diagnosed precip. So precipitation has a very different distribution than all of the other variables, and so we found that it's easier to actually have precip as a diagnostic model that's separate from the rest of the model. It shares the same backbone architecture as the original model, but it's computed separately as a function of the outputs of the first model. So precip is diagnosed, and once again, we compute a loss based on that prediction. So let's look at some of the results, starting off with the forecast skill, and just to clarify the terminology, on the y-axis is the anomaly correlation coefficient, which is a metric of weather skill used in medium range forecasting. On the x-axis is forecast lead time, and there are three different curves here, and I'll walk you through each of them. The first is the IFS, which is sort of the gold standard in global high resolution weather forecasting, which is the yellow line. An ACC of 1 is a perfect skill, and as you might expect, with increasing lead time, the ACC drops up to about 0.8 in about a week. And on the left for 500 hectopascal geopotential height, and on the right is 10-meter surface wind speeds. Our model in early 2022 was the pink line, and it had a smaller set of variables, and it was about a day and a half behind IFS at an ACC of 0.9. We're looking at the figure on the left here. And after we included a few more variables at a few different levels, we saw that the performance improved by almost 50% on geopotential height and more than 80% on surface wind speeds, and we're continuing to increase the training set. And we expect that perhaps one day we're going to beat or at least match IFS on medium range skill. So coming to the next property of the model, which is the potential to initialize this with different data sets. And this is a very exciting property of machine learning models, that you can potentially have zero-shot skill transfer by initializing the model from a different data set without retraining it on that data set. So in this case, we're looking at ForecastNet initialized using GFS versus ERA5. The model was trained on ERA5, so we do expect that it's going to perform slightly better. But we find that with GFS initial conditions, the model performs almost as good at the start, and then starts to taper off towards a week out into the forecast. Same is true for near surface wind speeds as well. And this is very promising because GFS provides initial conditions almost near real time, which means that we can actually have a predictive model that predicts the future weather, and not just one that's looking into history. So the next aspect of ForecastNet, which I mentioned, is the speed, and this allows us to create very large ensembles, potentially hundreds of members or maybe even 1,000-member ensemble. But such ensembles are only useful if they're well calibrated. So one of the metrics that's used in the weather forecasting community to measure the calibration skill of an ensemble is the spread error agreement. So here we're looking at the RMSE versus the spread on the y-axis versus forecast time. The green solid line is the RMSE of our model. in dots is the spread. IFS is the blue solid line, and the spread is the blue dots. And the calibration strategy that we use here is a combination of initial condition noise, and in particular, this noise is brown noise, so it's spatially correlated noise, and we expect dynamical systems to respond more favorably to noise that has spatial correlations of certain length scales. The second property is the model uncertainty itself. So we have a Bayesian model that perturbs the weights of the model. So the combination of these two uncertainty mechanisms gives us a pretty well calibrated ensemble, as we can see here. The spread scale agreement is good, and it also matches IFS. The next metric that's used to quantify the calibration of an ensemble is the CRPS, the continuous ranked probability score. And once again, here we're looking at CRPS on the y-axis versus forecast time. In blue is IFS, and in green is our model forecast net, and we're seeing good agreement there. So this gives us confidence that our ensembles are well calibrated, and this is essential for us to be able to trust the ensemble forecasts. So looking into some of the predictions, and there's a host of other figures in the paper, which is I think it was mentioned on one of the previous slides, but I can point you to it in the chat as well. So this is images showing the forecast at 96-hour lead time. On the top is the initial condition, and at the bottom is in the middle is forecast nest predictions, and the ground truth error 5 at the bottom. On the left, we look at an inset in the West Pacific, particularly looking at some tropical depressions that form into tropical cyclones 4 days later. On the bottom, we see this super typhoon Mangkhut, which was a pretty impactful event that's captured quite nicely by ForecastNet, including the intensity as well as the trajectories of the tropical cyclone. On the right is an inset in the Atlantic, and there was this really strange phenomenon of a series of hurricanes forming one behind the other, Florence, Isaac, and Helen. And this is also captured quite nicely by ForecastNet. So we get into more details in the paper on the prediction scale with regards to the trajectories of these hurricanes as well as their intensities. And we've looked at also atmospheric rivers, extratropical cyclones, and various other types of events. So one fundamental question about all of machine learning is the ability to predict more accurately the fine scale detail, and it's been a challenge for all machine learning models. And generative modeling has been the approach that has been quite successful in improving the sharpness of a forecast, so capturing the fine scale details. And this is some early work from Lawrence Berkeley Lab. Our collaborators at NERSC have developed a combination of ForecastNet with an adversarial loss, so something like a generative adversarial network that can help sharpen the fine scale features. So on the left is the original ForecastNet with just the regular L1 loss. In the middle is a combination of the adversarial plus the L1 loss, and on the right is the ground truth. As you can see, the middle image is much closer to the right in terms of the fine scale detail. Now looking at the quantitative impacts of what that fine scale detail provides, well, the biggest benefit is that it helps in capturing extreme precipitation statistics much more accurately. So on the left is a plot of ForecastNet, and we're looking at the extreme percentiles of precip here on the y-axis, on the x-axis in log scale. On the y-axis is total precipitation. The original model without the generative modeling is the red curve. As you can see, it underpredicts extremes. IFS is in blue and the ground truth error 5 is in black. When we include the adversarial loss on the right, we see the red curve moves much closer to the ground truth. So we're now capturing extremes much more accurately. So this is quite promising, especially when we come down to regional scale predictions. Now, perhaps the most interesting for this audience, given that it's a climate audience and not so much weather forecasting, we care about long-term predictions for climate. And of course, if we want to have a full atmospheric emulator, we want it to be stable and have the right dynamics over long periods of time. And one of the characteristics of our original model is that it uses approximations about the periodicity of the domain using the 2D FFT, which are not quite accurate because the Earth is a sphere, and we really should be using spherical harmonics. So we've now started to develop a spherical harmonics-based neural operator approach, also along with transformers, and we're starting to see significant benefits in the stability of the model. And here, I'm not going to wait for the video to play. It's probably going to take 5 minutes, but you'll have to take my word for it that the model is stable out to about 250 days. So we're testing the properties of the model, and in particular looking at the spectra and whether it characterizes the dynamics accurately over long periods of time. But this is very promising with regards to looking at long-term emulation of the atmospheric system. So as I mentioned at the start, one of the nice things about combining Fourier neural operators along with transformers is that it produces an efficient and highly scalable model. And in particular, we've looked at scaling the model out on different supercomputing systems. These are scaling plots for 3 different systems: Joule's Booster at the Jülich Supercomputing Center, Perlmutter at Lawrence Berkeley Lab, and Selene, our in-house supercomputer. And in all 3 cases, we find that the model scales quite nicely out to about 4,000 GPUs. The advantage of scaling these models out, of course, is that you can train the model much faster. So the training time decreases from about 24 hours to just about an hour, but also that you can scale these models out to larger data sets and higher resolutions. So we're looking into training the model on 10-kilometer data and potentially higher resolutions as well this year. Okay, so I want to summarize some of the biggest benefits of ForecastNet, which is its speed, besides the fact that it's very accurate. And the speed enables the computation of large ensembles that are well calibrated with a much smaller energy footprint. And here is a table that shows the comparison between IFS, ECMWF's global model, versus our model. ECMWF requires about 3,000 nodes to make a 100-member ensemble forecast. Actually, they only make about 51 members at this point. Versus ForecastNet, which requires a single node for a 100-member ensemble forecast. And so the relative ratio is about 1,500 times less in terms of the nodes required. The number of node seconds required for this computation is about 1 million for IFS and about 7 for ForecastNet. So that's a 45,000x speed up. And correspondingly, the energy savings is about 12,000x. So the speed up and the energy footprint reduction are 2 very attractive properties that enable us to use very large ensembles, and we're exploring the implications of this. So I'd like to touch upon a few things that are brewing right now, which is moving away from weather towards climate. There's still a fair amount of work to be done on the weather extreme, but we're looking towards climate emulation at longer timescales. So I want to bring back this figure that Bjorn Stevens proposed last year at the GTC keynote that he gave. So if you have one of these trajectories of these very high resolution numerical simulations at, say, kilometer scale for over 300 years, one challenge is that, of course, it produces a humongous volume of data, about an exabyte of data. So one way in which you could use models like ForecastNet, emulators of the atmospheric system, are to use it to essentially interplay between checkpoints of your model. And so you can only need to output your model outputs at much lower frequency, say once every week, or maybe once every 2 weeks, or maybe even once a month or so, and use a machine learning emulator to essentially fill in very rapidly between those checkpoints. So this is what he calls tethering, and fast tethering is one of the ways in which ForecastNet could be used. But also you could imagine ForecastNet being conditioned on different climates. So we have different trajectories here, and you could train ForecastNet to respect the different trajectories in terms of having a conditional model that is conditioned on the climate scenario. And then you can have not just an interpolator, but also potentially an extrapolator. So that's one way in which we're exploring using ForecastNet in the climate context. And as I mentioned, one question that is really exciting is that is this just a weather emulator, or could it potentially become a climate emulator, meaning that it could roll out to maybe months or even years? And if it has the right properties, that would be very interesting and have huge implications for climate modeling. So here's a roadmap of the things that we're doing with ForecastNet, but also with many other models. On the left bottom half of the figure is the work that we've been doing on the weather extreme. So we have results from early last year, or I guess mid last year, on real-time weather forecasting. We've calibrated our ensembles. In October, in December, we've scaled these models out to get close to the IFS gold standard. We're continuing to push that boundary. We're starting to develop regional versions of the model. So you can imagine having a nested, much higher resolution model within a global 25-kilometer model. And this is an exciting avenue and could potentially help democratize regional weather forecasting. But moving on, we're starting to focus on climate, and one of the things that we're starting to do is train ForecastNet on the high-res MEP archive, which has many different models at 25-kilometer or coarser resolution, and this would be a good test bed for us to test some of the ideas on tethering. But further ahead, we are intending to train the model on 1 to 10-kilometer scale simulations to do tethering at higher resolution. And we recently have, well, actually, it's been about 6 months plus now that Mike Pritchard has joined us, a professor from UC Irvine, as the director of climate research at NVIDIA, and he's developing a very nice climate strategy for accelerating climate simulations using many different ideas, from spatial coarse-graining to multi-scale modeling and so on. And in combination with some of these approaches, we could imagine ForecastNet providing much higher speed ups on climate simulations as well, going on to sub-kilometer scales. So as I mentioned, we're starting to train on the 25-kilometer and coarser resolution data sets from the high-res MEP archive. And this is an example of how that might look like. On the left are the different scenarios from this data set, and we train ForecastNet conditioned on these different scenarios, and then use it for data-driven tethering, potentially up to 2 weeks, or maybe even much longer, depending on the stability of the model. And this can be used for very fast analysis and projections for various different types of applications, whether it's renewable energy or extreme events or disaster mitigation and so on. But eventually we want to tether to kilometer scale and sub-kilometer scale predictions, because we know that the cloud feedbacks and storm dynamics are only reliable when we actually get down to these scales. So that's the sort of next frontier that we're looking at. Okay, so I want to wrap up in the next few minutes with some of the technologies that we're developing to support all of this work. So Earth-2 has sort of the science and the machine learning, and underneath is all of the engineering that comes with it, which is the many different platforms and the full stack technologies that NVIDIA is developing to support the building of digital twins. There's many different technologies, and I'm only going to mention 2 of them. One is called Nimbus, and it's very early stage, but very exciting. It's an end-to-end machine learning operations MLOps platform. And for those of you that are not aware, MLOps is very important because these models need to be trained many different times. Their hyperparameters need to be optimized, and we need to have an end-to-end pipeline that allows the training rapidly and automatedly in an automated fashion on many different data sets. So this is a huge engineering challenge, which I think most of us in machine learning face. The pre-processing, the ingestion of the data, the training, the inference and deployment, all of that needs to be highly optimized, and an end-to-end pipeline to do that is going to accelerate the pace at which we can do our research. So that's the platform that we're developing. It's going to be hosted on the cloud. It has an API for easy access to various different data sources. Some of the standard data sources, such as the CMIP6 archive, RF5, and others, but also observations. It leverages the physics machine learning framework that I mentioned earlier, Modulus, and also various other AI and performance optimization tools that NVIDIA has. It's designed to have fast inference and deployment, and we will also be hosting a range of different pre-trained models, including ForecastNet, that can be used for transfer learning and potentially also for building foundation models. And finally, recipes for developing different types of models and fine-tuning them for different applications, such as regional prediction and specific phenomena like extremes. So stay tuned for more on Nimbus. The second is Omniverse, which also I briefly mentioned at the start, which is a platform that allows scientists and various other experts to collaborate together on building digital twins. And this is already being done for various other technologies like automated vehicles and designing engineering systems and so on. So we're adapting it for Earth system science applications. The basic idea is that there is a central shared space where models, data, tools, services, and applications can synchronize. And the key thing is to provide low latency. So to be able to move data or have data be essentially simulated on the fly using machine learning. And one example of this would be, for example, here we have an image from Icon on the top left at high resolution. You could have data streaming in from Icon. Have machine learning models that are providing simulations on the fly. On the bottom left is some data analytics, for example, using Pangeo, provided also through the nucleus. And on the top right are observational data streaming in to update the digital twin, maybe archives of climate data coming in from the CMIP6, for example, and finally a range of different impacts models that are harvesting all of this data together. So of course, this is a very ambitious concept, and it will probably be a year or two before we can actually have working models of this, but the various different pieces that go to building this technology are already happening right now. Okay, so with that, I would like to conclude saying that this is the work of a very large team. Many of us at NVIDIA have been working on this actively for the last year or so, including Mike Pritchard, Anima Anand-Kumar, David Hall, who was actually at NCAR previously, and several others. And it's also in collaboration with many other universities and institutions across the globe. So thank you very much, and I will take questions.
Hey, thank you very much, Karthik. So looks like we have a question right off the bat. Oh, a couple. So I saw Jerry's hand go up first. So Jerry, feel free to unmute, show your face, and go ahead and ask your question.
Okay, so thanks a lot, Karthik. That was really interesting. I think one of the questions that out to about 250 days now before it blows up, and I know that from earlier talks I've heard that used to be almost a week, but now it's out to 250 days, which is really good. But what actually causes it to blow up? Is it just that the model, you're forecasting timescales that are beyond what you've trained on, or what makes it go unstable and blow up?
Yeah, so I think I mentioned this briefly, but the reason it was blowing up previously after about 2 weeks was because we were using the 2D FFT, which doesn't respect the geometry of the globe. And so we start to see instabilities crop up at the poles, which is where we basically break the spherical geometry, and then that percolates through the domain, and then finally it all explodes in about 3 weeks. So once we've moved on to spherical harmonics, which is very recent, we're starting to see that we actually obey the geometry much more accurately, and now the model is stable out to any number of days. We've only run it out to 250 days, but I imagine it would be stable longer than that too.
Okay, thanks.
Okay, thank you. So Judith is up next.
Thank you very much. Very interesting work. I have a question and a comment. My question is, could you say a bit more if you're learning the variables in the different levels separately, or are you learning the actual column, including all the state variables in the column? And my comment is, I really think in terms of ensemble forecasting, even if your model is not as good as the IFS, if you can do 100 or 1,000 ensembles, which is something you can do, you can greatly improve probabilistic skill in extreme events. And this is sort of a no-brainer, low-hanging fruit, and I highly encourage you to exploit that more, because especially for extreme events, etc., across the scales, it's very, you get a lot of bang for your buck.
Thank you. Yeah, great comments. So responding to the first question, we're learning the whole thing in one shot. So we're not learning individual variables separately. All the variables are being learned simultaneously. So we do expect that correlations between the variables are also being learned, although we haven't tested this in our forecast. So whether different variables have the right covariance over time. So that's hopefully that addresses your question. Maybe digging into that a little more, if we try to think about the vertical structure, we haven't looked at the fine-grained structure because we only have 5 levels. But I suppose that there is something being learned about the vertical structure as well in the column. And this is to be tested. The second point, fully agree. I think even if we don't have the same deterministic skill as IFS, the power of having a 1,000-member ensemble to capture extremely rare events is huge. And yeah, we'd love to explore this in collaboration with you or others that are interested in this. Did that answer your question? Great, thank you.
Right,
you.
thumbs up. Okay, so Julio?
Karthik, thank you. I'm wondering what the obstacles are to doing something like attribution studies with ForecastNet. So, trying to quantify the effects of, let's say, thermodynamic changes due to global warming and individual events.
Yeah, that's a great question. The obstacles, I think the first obstacle is that we don't have a climate aware model yet. So it's not conditioned on the climate. We're currently training on all of Era 5, and of course the climate has changed in the last 40 years, but the model has learned that change over the entire data set. I think a more sort of nuanced approach to doing this, to address your question about attribution, would be to actually train the model as a conditional model conditioned on different climates, so it understands the difference in the dynamics between different climates. And as I mentioned, that's sort of the next step that we're taking with the high-res MIP archive, is to train ForecastNet on various different climates and provide either a single parameter or maybe an entire field or multiple fields that allows the model to learn what the climate is. So we could reduce it down to simply the concentration of CO2, but I think there's probably more elaborate ways in which you could condition the model.
Thank you.
Okay, and we've had a couple comments and questions come in on the chat. So Brian, I don't know if you want me to read your question or if you want to unmute and ask.
Sure, I'm happy to ask. Yeah, this is, again, just my, good to see you, Karthik, my general skepticism that you're used to and my lack of understanding here. Given how impressive these results are compared to the IFS, what is the trajectory for having this be used for operational forecasts for weather in the future? And, why isn't that on the, near-term future?
Yeah, great question. I think well, I'd say one of the biggest steps is to really apply the full suite of verification and validation techniques that, say, ECMWF or NOAA or others use. And if you go to the ECMWF website, they have the scorecard with 300 different metrics that they apply to their forecasts, everything from skill of different variables to covariates to extremes and probabilistic scores and so on. So I think actually applying the full suite of diagnostics and verification techniques is something that we haven't done to ForecastNet. We've done a little bit of analysis on the extremes and the ensembles. We've quantified the skill. I showed the results on the calibration, et cetera. But really piping it through what operational models are done, are piped through today is probably the next step to build trust in a purely data-driven approach. I guess the next thing would be to look at regional phenomena. So do we actually capture characteristics of extremes in specific regions, or even average skill scores over a specific region of the globe? Because most of the metrics that I showed you are global metrics and not regional metrics.
Thank you.
Okay, great. Thank you. And looks like Andrew has a question, so I'll take yours now.
Okay, can you hear me okay?
Yes.
Thanks, Karthik. That was really interesting. I guess I'm following up on Brian's question. Sort of two questions. The first is pretty quick. If you didn't have ERA 5, in other words, if you didn't have the assimilation system and the sort of truth, you couldn't do this, right? I mean, you need the physical modeling system to actually build the forecast net, right?
That's right.
So, and then your comparisons were, again, you're comparing the IFS, which is a forecast with the same system sort of as ERA 5, to just training on the present day state, right? That's what you were looking at. And you could get almost as good as the IFS, but not quite there. But I guess theoretically, you could be better than the IFS, right? But you still need some sort of underlying modeling. You still see some sort of physical digital Earth to actually create the current state of the planet, right? With observations and assimilation and all that.
That's right. Yeah, we're dependent on data assimilation to get our initial conditions.
Okay.
But
yeah,
maybe if I preemptively could say, I think maybe you're going in the direction of, is there a way to replace the data assimilation itself so we can go straight to the observations to create an initial state? So you're not actually using the data assimilation system. Is that where you're headed?
That's sort of one question. It wasn't where I was headed, but you can answer that.
Okay.
I think that's a very interesting comment. Yes.
Yeah, no, I think there's a lot of work going on trying to use machine learning to replace or augment data assimilation. So you can go straight to observations to create your initial state as against using, say, 40 bar or something else. But that's not there yet. So we're still dependent on initial conditions coming in from DA.
Okay, thank you. Very interesting.
But maybe you had something else in mind.
No. There is a lot of work on incorporating machine learning into the DA systems, but there probably has to be some sort of physical model behind it to do all the constraints to get the system balanced so that it doesn't, I don't know, maybe not. But it's a very interesting thing to pursue. So I know machine learning is going into a lot of it, is starting to be explored in the DA systems for a lot of the different pieces of it. But thank you.
Thank you.
Okay, thank you. So Rich, I'll take your question in a second. I'm gonna quickly, or is it a follow-up? Okay. Christine, if you're on, do you wanna unmute and ask your question? Perfect.
Hey, Karthik, that was a great talk. Very exciting stuff.
Thank you.
This is actually, it sort of follows on to the previous two questions. And we were talking about the different systems that you initialize with. You hinted about this a little bit when you said that the errors that that ForecastNet had was probably likely due to the fact that it was a different, you ran the model with the initialized with a different system that you trained it on. So I was just curious if is that due to resolution, and if so, what types of errors do we see there, or how big are they, and how do you mitigate that?
Yeah, great question. Yeah, it is. It's not because of resolution. We actually have the same resolution initial conditions coming in from GFS, but it's our leading, or I guess our working hypothesis right now is because it's because of different distributions from the two models. So GFS has a slightly different distribution for the different variables compared to ERA 5. They're quite close, but not quite the same. And in machine learning, I think the sensitivity to distribution shifts is quite high. So even if you have small distribution shifts, your model can start to behave less skillfully than it is in the training set distribution. So one way to mitigate that would be to fine tune with a little bit of data from GFS. So it learns that distribution shift between GFS and R5. And this is also, I guess the underlying cause, the distribution shift, is also the main reason why machine learning models don't extrapolate. So this is sort of a small extrapolation problem that it's dealing with, but a much larger one would be under climate change.
Thanks, Karthik.
Yeah, thank you.
Okay, so let's take Rich's question next. Then we have one from Andy Wood that we'll take and finish up with Brian Dobbins' follow-up. Okay, Rich.
Yeah, thanks. Yeah, it was a nice talk. I'm just wondering, you said you trained on ERA 5 6 levels, I think, originally, and I'm wondering, how you decided upon those levels. Is it pretty arbitrary, or did you test a number of different levels? Because one could imagine, the atmosphere is some singularity, close to singularities with the boundary layer, for example, where 600 millibar high is probably not that interesting, but closer to the surface is probably more useful.
Yeah, exactly. Yeah. I didn't give the full history of how we went through the sort of development cycles to get to where we were at. But we've gone through something like at least 6 or 7 different design cycles. We started off with just the surface variables. So we only had winds at the surface, precipitation, sea level pressure, and I think a couple of others. And then we started to add variables starting upwards from the surface. So 850 hectopascals. And then we said, okay, well, maybe we want to go to 750 and then 500. Turns out that information at 250 and 50 are also quite useful, especially for some of the longer range events. So yeah, it was sort of a progressive addition of levels, somewhat trial and error based, but also driven by intuition.
Okay, thank you. Andy?
Yeah, thanks. Fascinating talk. I just was curious when you were showing the generative modeling component that improved the skill of the extremes, and you're showing that definitely improved the amplitude and the CDF summary statistics much better, but does that also include the spatial pattern skill? I'm kind of wondering how well that works for spatial disaggregation. Can you do skillful downscaling from the model grid scale with that? Thanks.
Yeah, that's a great question. No, we haven't looked at the spatial distributions and in particular whether it's got the right spatial characteristics as extremes. I showed the images where we do sort of visually see that, but I'm sure there's more quantitative ways to explore that. And maybe a follow on to that point is that also the temporal evolution of those fine scale features. So does it actually do things at the fine scales evolve temporally in the right ways? Because these generative models are generally not great at doing that.
Great, thanks. Yeah, great stuff.
Thank you.
Okay, thank you. And we have a follow-on question from Brian. Do you want to unmute
Sure. Yeah,
and ask that? Perfect.
Yeah, this was purely computational. I know from your paper that you're using a mix of precisions. You mentioned this in the talk. I'm curious if you've quantified the differences you get if you, for example, ran everything in FP64, it'd be less efficient, or if you did the weight updates in FP32, when does that trail off in terms of accuracy? I'd just be curious if you have any data on that.
We haven't done exactly that study of comparing the performance with different precisions. But one thing I'll say is that we can still go lower. So there's actually some recent work on FP8, which is starting to show promising results as well. So because these machine learning models are learning statistical properties and they're all stochastic models in some sense because of the ways in which they're optimized, I think there's still a lower precision that we can go to potentially FP8 as well. So we haven't hit any saturation point yet.
Great, thanks.
Okay, are there any additional questions? If so, you can raise your hand. You can also insert it into the chat. am not seeing any questions, so I might just choose to conclude our CGD seminar for today. Thank you very much, Karthik. That was a very intriguing presentation, and some great discussion followed. So thank you again for joining us today. And we will be back on the 17th with our seminar by Lorenzo Polvani. Okay, thank you.
Thank you very much.
Okay, and I think we'll just wait for everybody to drop off and then end the recording.